So you said you're working on homework 9 and it's going good, right?
Yes, yes.
Okay. So remember homework 10 is midterm 2, right? And as of here, it is saying April 8th, but let me know if there is a need for postponing or anything. Homework 11 is due April 8th again. And that's primarily because I wanted a few more homework sets to come in so that in a few weeks you can finish it up. But it's all flexible. We are just one student basically. Harsh, I don't see him anymore. So, so just let me know whenever. But remember, you will hit a wall.
Yes.
Yeah. You manage it, be responsible, and you have been very responsible as of now. So I'll leave it to you. Okay. But it's clear how many homeworks are going to be there. There are going to be 3 more homeworks after this, and there is this midterm. You put it be according to your convenience and make it you on your own. Okay. So we were talking about the Kepler problem, right? So we're talking about the Kepler problem, and what we have here is we have a mass m1. There's another mass m2, and that could be some coordinate system in terms of which this position is r1. The position of m2 is r2. And the interaction energy depends on the magnitude of r2, let's say r2 minus r1. Since it is a magnitude, it really doesn't matter, but yeah, we defined it as r2 minus r1. And that's equal to the gravitational potential energy G m1 m2 over r2, let's say, minus r1. And that's your r2 minus r1. That's also the center of mass somewhere here. Doesn't have to be exactly at the center. There is a center of mass as a position capital R. The Lagrangian for this is half m1 velocity v1 square plus half m2 v2 square minus of u, where u itself is negative, so it becomes positive. Eventually, it is not the energy. Energy requires this to be plus, right? Kinetic energy plus potential energy is the energy. So this is the Lagrangian. We defined coordinates R, the center of mass coordinate R1 plus M2 R2 divided by M1 plus M2, and we define R. Is equal to R2 minus R1. And in terms of that, notice this Lagrangian here, L depends on R1, V1 or 2, V2. So in terms of the new coordinates, it's expected to depend on the position of the center of mass, the velocity of the center of mass, the relative position between the two masses, and the relative velocity between the two masses, or not the relative velocity, the velocity associated with the relative position, which will be the relative velocity. And in terms of that, we showed that this is half m1 plus m2 v squared, capital velocity v squared. And then we defined half of a rest mass mu velocity v squared, where rest mass mu is defined as 1 over m1 plus 1 over m2. And minus of u of r. Notice it does not depend on the center of mass of the object, so this is not there. And if I were to choose a frame in which velocity is 0, right, since this is going to be going with constant velocity, this does not, the rest of the Lagrangian does not depend on the capital V. That means it's V is a constant. So I can go to the frame in which V is equal to 0, and this can be killed. So choose V to be equal to 0. So again, V is a constant because derivative of velocity will be 0, or the momentum associated with this capital R will be 0. So once V is a constant, then I can go to that frame. If V was not a constant, then I cannot go choose such a frame. So choosing that gets rid of V also. And in that particular frame, I have the Lagrangian to be dependent only on 2 coordinates now. Velocity, position, relative position between the 2 objects. So, and our Lagrangian then is half mu velocity squared minus u, or significantly simple. Oh, I'm supposed to be changing this also. Okay, that's good. So then we showed that the angular momentum L. Now this is a little confusing. This is the Lagrangian L. This is the angular momentum L. Both have the letter L, but this always shows up as a vector unless you do a magnitude of that. And after a few steps, we will start writing the magnitude also, but at that time we'll stop writing the Lagrangian. So hopefully in the context it is very clear. So we will, it's easy to choose another letter for this L, but it's also standard to have angular momentum as L. So it's a bargain, you write, and I say that let's live with this. It's only a little confusion. In the context it is very clear. So angular momentum is R cross P. And angular momentum is conserved in this problem. And that can be seen very immediately because it depends, because the potential energy, or for that matter, the whole Lagrangian, depends only on the magnitude of R. Remember, if you were to do the homework regarding conservation principles, we showed that if angular momentum has to be conserved, how do you look for it? What symmetry corresponds to that? It should not depend on any angles, and this does not depend on any angles. Right? That's immediately a signature that angular momentum must be conserved. So you go and find that out. And indeed, we showed that that's equal to 0. If that is equal to 0, then we can choose L to be in the direction of the z-axis. And it's also noted that we also showed that R dotted with L, the position of the object is always perpendicular to the angular momentum. So if that is the case, choose L in the z direction, and we can have R will be in the xy plane. So there is only theta and phi, only R and phi, the polar coordinates that comes into picture. So L can be further reduced, choosing L to be L in the z direction. So choosing L to be in the z direction, we have R and phi to be the only variables representing dynamics. So that's R dot, so phi dot. So only possibility is that it's in a plane and the radius can change and the angles can change. Right? So, and we also showed that phi has to keep increasing. It cannot retrograde, right? Even though we see planets going backward in time. Is that familiar concept? Like around the sun, everything goes in a circle, correct? So if you stay on the sun and watch every planet, it will keep increasing the angle. It will never go backward, right? But if you're on Earth and look in the sky, let's say Mars, sometimes it goes backward. Are you familiar with that? It's called retrograde. So look it up. So retrograde motion. I think it happens every year, once in a year, I think, or it depends on it. Probably not just years. It depends on where Mars is, what is the relative velocity between Mars and Earth. Imagine you're sitting on Earth. Since Earth has a velocity, Mars also has a velocity. You can always imagine when you're overtaking Mars, then Mars is actually going backwards. Right? So for a small period of time, you will see that, oh, Mars is going backward, and then it will go forward. So that's the complication that comes with Earth as the center, right? Remember Copernicus and before Copernicus, when Sun was not the center, they had to deal with all this retrograde motion, and they knew how to do this completely. They knew all precisely everything used to work out. It's just that it was a complicated system. So that leads to a good question as to like this is what I typically ask. What is at the center? How do you know that Sun is at the center and not Earth is at the center of maybe like Earth? Suppose I claim today that Earth is at the center and Sun is actually going around. We see it, right? It rises and it moves. So why should I believe anything? Why should I believe the books? How do I convince myself that actually Earth is moving and Sun is at rest? How would someone convince themselves, or let's say I convince myself? So how would you do that? Please. Like how did Galileo convince anyone? Like it was Copernicus who said this, but then Copernicus did not get or he was more careful. I think he did not get into arguments, but Galileo got in trouble for that. Mm-hmm. So there was a good enough reason in the sense no one Earth is going around, right? So interesting fact is that yes, it cannot be proved very easily. So one of the claims of Galileo was that it was not very convincing, is that he showed Jupiter. He was the first person to use telescope to look up in the sky, at least written knowledge. He was the first person to look up. And he saw that around Jupiter, there are moons going around. So have you seen Jupiter through the telescope? So if you see the Jupiter, you see small dots, right? They're static usually when you see it, but if you do if you look for hours, for example, it doesn't have to be days. If you just look for hours, they move. These dots move. And then you realize that, oh, these are all actually moons of Jupiter. So the only argument, or one of the major arguments early on Galileo had, was that, see, you have another object around which things are going around, so why can't you have Earth going around the Sun? Which is not really a strong convincing argument. But later on, of course, things got better, and the only reason you can give, which is a pretty sophisticated argument is that if you look for phases of Venus, phases in the sense like moon has this, what do you call it? Do they call it phases? What the crescent of moon is having a certain direction, right? And if you want to explain that, or crescent of moons can be explained easily, but if you want to explain the crescents of Venus, because Venus is inside Earth, the only way you can justify that is that it must be the sun must be the center. I myself have not gone through the argument. I mean, I followed the argument, but it seems like, okay, I might have missed something.
Yeah, I've done that.
Yeah, so that's
it's the comparison between Venus and Mars. So when you see the difference in the phases, that's where you come to the conclusion that one is outside and one is inside.
Okay, perfect. And that cannot be explained using that. And what did you do on this?
The phases.
Yeah, but what is the project you did?
Oh, it was actually for 101 lab. And
okay.
So they showed you phases taken between the whole year, right, at almost every quarterly period. And they showed the phase of Mars, and then they showed the phase of Venus. And then you have them both in orbits. And you can write the phase of how they are perceived from Earth, and then how they would be perceived with the light from the sun.
Okay.
And they coincide.
Is this experiment going on here? Okay.
Yeah, that was for here. Yeah.
I should talk to Dr. Henley. Yeah. Okay. Good. So, having said that, since we are having this discussion, it's a digression anyway. But so, is there any experiment you can do on Earth? Like you can ask, okay, if this is such an important deal, let's say at the time of Galileo, or even today, what is an experiment you can do sitting on Earth in your lab, which will conclusively tell you that Earth is moving up the sun? Like, is it possible to do such an experiment?
I would say so, yeah.
So that's a quiz. Okay. Is that sitting on Earth, what experiment do you think can tell you that it is the Earth that is moving and not the sun? And it's not easy. It turns out it's not easy. Like, yeah, I'll leave it at that. Okay, so we have this coordinates, and we said that that's equal to half mu dot square plus, so the kinetic, and there's a kinetic energy associated with the r motion, there's a kinetic energy associated with the change in angle, right? And then there is a potential energy, which is minus u of r. But then there is still angular momentum is conserved, so there is still one more quantity that is conserved, and that is the dl by d phi dot. And we said that angular momentum in the z direction, but angular momentum is completely in the right. So this is angular momentum. Let's write LZ for now. So LZ is mu r square phi dot. That's equal to a constant, which immediately tells us that, oh, I can replace phi dot now. So there's only one parameter, then that's just radius. So how far you're from the Earth decides the motion completely. R and R dot gives you everything for the problem. Okay, so choose that. So, so with that in mind, we also showed that energy E, there is another constant. Angular momentum is of course constant, but there's also energy that is constant, and we showed that if we were to define mu or dot square plus if you want, this is a constant, so I can always say, so this is mu or square phi dot square and minus plus u of r this time is equal to a constant. Right? This is equal to a constant. That means total derivative of E is a constant. So let me take this. So a summary is that we have a Kepler problem independent of, I have not even said, so really use the fact that this is 1 over r. This could be any r. This could be 1 over r square, 1 over, or even proportional to r. Like think of a harmonic oscillator, spherical harmonic oscillator problem. Any r dependent problem we have shown. First, we have shown that angular momentum is conserved. The L by dt is equal to 0. And second is that energy dE by dt is equal to 0. This implies that things will happen in a plane, right? The motion is going to be planar, which further implies, which we haven't shown yet, but it will imply that it has to be a conic section. So either it has to be an ellipse or a hyperbola or a circle or a parabola. So that's the conic section. That's good, and that's intuitively clear. Energy is equal to a constant. That means that if you start with a certain kinetic energy, that decides your size of the ellipse, right? What's the eccentricity of the ellipse, right? So how squeezed the ellipse will be. So this decides your eccentricity of the ellipse. Okay. And this is for any u, right? Any potential. But there is this nice feature. This is what your homework is about. For u is equal to minus alpha over r, that alpha is g m1 m2. That's your gravitational potential energy, or for that matter, this could also be hydrogen atom, right? If you're doing classical hydrogen atom, classical means if you're not doing quantum, right? That's the same interaction, right? Electrostatics and gravitational potential energy, there is no difference. It's just the constant changes. And then it turns out that there is another constant. Okay? So there is another vector, so that's your third one. This is only for this potential, not for 1 over r square, not for spherical harmonic oscillator. Only for this, there is a third vector. This is dA by dt is equal to 0, and that is equal to what is yeah, I want to enter. Yeah, let me not yeah, instead of giving you the formula, so the point is every time there is a constant, there must be an interpretation, right? As we have planar eccentricity. And here what happens is that if you were to think of an ellipse, you could ask the question that if you have an ellipse, is it possible that this, think of this as an egg, right? As time goes, this ellipse itself is rotating around. Right? So, for example, is it possible that for this potential, you start from here, go here, and then goes like this, It's called the precession of the perihelion. Perihelion is this point here, extreme point. Is it actually moving around? And planets do that. And if you have heard about perihelion of Mercury, that is one of the proofs that is used for general relativity. Why Einstein is right. Mercury actually slowly rotates and all that. Historically, what happens is that again, all this is kind of nice. Newton gave his gravitational potential energy, and immediately after that, they started predicting things. They started looking at the sky, and almost everything could be explained to one or two or probably third significant digit. I don't exactly know how much, but we are talking about really the perihelion of Mercury. Right? And to the extent that if you cannot explain it, that means there must be some mass there. Notice the argument here, like what earlier the point was, okay, you first look at it and now you're able to explain it. And if you're not able to explain it, there must be some mass there, right? There must be something else influencing. And this was very successful. For example, Pluto, they never could see Pluto very well. But they did notice that, not Pluto, I think it was Neptune. So they knew Pluto, and they noticed that Pluto's orbit was not matching with whatever they know. If you accommodate for all the planets, its orbit was not working very well. And Neptune is so far away that sometimes it is too far away that you don't even see it. So it was claimed that just based on the orbit of Pluto, I might be wrong with which planet I'm talking about, it might be Neptune or Pluto, they could predict that this planet existed, and then they looked for it and they found it, right? So that was remarkable, like achievement there, right? I mean, you're able to predict that there is something. Similarly, Mercury's perihelion cannot be explained until 1905. And when you cannot explain something, what do you say? There must be a mass, right? So there the prediction was that there is another planet inside Mercury. So Mercury is not the first planet. There is another planet in the inside orbit of Mercury, and it is so close to the sun that we are never able to see it. Our sun is so bright, we are never able to see it. And that's what the point was. And this was all the orbit for that planet was given so that it explains Mercury's perihelion. But then Einstein came and said, oh, this has nothing to do with that. It is just that if you take care of relativistic corrections, that works. So the stories are pretty nice, where sometimes you get very confident with the theory and you start predicting, but then you can fail also in those predictions, right? So it can go either way. So that's what we are talking about. And it turns out that if this is the only potential existing, so if 1/r is the only potential and this is a two-body problem, then this is zero. This doesn't precess. If there is only only two masses, then the axis, so A is the direction of the ellipse. So that's your A. And this is called the Laplace. It was Laplace who first noticed this. Laplace-Runge lens vector. Now that's conservative. And in your homework, you will show that this is actually zero, which means that there has to be some quantity that is conservative. And somewhere else you can, actually it is very nice because when you do hydrogen atom, this plays a very important role in getting the energy quantum numbers. So first time the hydrogen atom was solved using this number. Okay, but we are interested in finding the orbits of associated with the Kepler problem. Very soon we will use this. We will specialize to the Newtonian gravity, but at this point, let's keep it for a few more equations, let's keep it general. So we have energy to be conserved. So let me start again with this equation. So I have 1 by 2 mu dr by dt square is equal to, let me write this one all on the other side. So that's E minus U of R and minus of, replace this with the angular momentum. So phi dot is having mu R square, but I have to square that. So I will have LZ square. Right. And divided by a factor of 2 mu R square. And I square it, two of the R squares cancel. Okay, so that's what it is. So I can, let me process this a little bit. So dr by dt is equal to 2 over mu, right? So it is 2 over mu times E minus U of R and minus of, I'm multiplying by 2 over mu, factor of 2 cancels out, mu cancels out, so that's LZ square over R square. Is that correct? Yes. And that's square root. I think this is where we left last time. And we also replaced dt. So dt would be equal to dr over, everything here is r dependent, so it's good to put this on one side. So it's 2 over mu U r but using the angular momentum conservation, I can connect dt and d phi, right? That was what told us that angle is monotonic with respect to time, so replace dt with angle d phi. So this we immediately replace this with d phi will be dt over mu r square, or dt will be mu r square. No, d phi by dt, so it's dt is mu r square. No, d phi by dt. Yep, so this is d phi times, so mu r square d phi over LZ. Using this equation, d phi by dt is mu r square LZ. So this LZ is equal to mu r square d phi by dt. So replace dt, so dt is equal to mu r square d phi over LZ.
I think you're missing a mu.
I'm missing a mu?
A mu squared under the LZ square.
Under the LZ square. Okay. And why did I miss that? Okay. I thought here I was okay because this is okay, right? This
Then
is,
then you divide by mu again, right?
so I divide by a mu. Oh, so that's mu square. Gotcha. Good. Thank you. Okay. Okay. Thank you. Okay. So we got d phi is equal. This is where we left off. So mu z or LZ over mu r square d phi of dr 1 over 2 over mu e minus u minus Lz square over mu square r square. One more thing I'll do, I'll take the mu inside. I think probably we did that also last time. And then what we get is phi is equal to Lz over Lz dr over r square and 2 over then I multiply the mu inside. I'm taking the mu inside the square root. That becomes mu square. This becomes 2 mu e. And this becomes 2 mu u. And this is minus Lz square over r square. Remember, what are we looking for here? We are interested in r as a function of time, but we gave up time and we said time phi is good enough. So if we integrate this, we get a phi there. If we integrate this, we get a function of r. And that means if I invert that, I get a function r as a function of phi. So once I'm done with this integral, I've solved the problem. Right? I've got the orbit basically. Right? So that's what here. Trying for. So at this point, let's specialize, right? Until now, this is very general. We are saying, which is good. We'll start this again when we talk about a perihelion of the object due to some perturbation. And here, let's specialize to u. So now let's say u is equal to minus alpha over r. That alpha is g m1 m2. It is minus, so this becomes plus. So this is d phi is equal to Lz r over r square 1 over 2 mu e plus 2 mu alpha. Let me apply, so let me leave some space here. So I'm saying this is plus 2 times mu, and this is 1 over r, or alpha over r. So let me write this as mu alpha and 1 over r. I'm leaving this space here. I'm going to do something manifold with this, right? And this is minus Lz square over r square. And this is a square root, everything inside a square root. If you want to probably write it in 2 different steps. Okay, so what am I planning to do here? I want to make this a complete square, so that is Lz over r square, so I multiply and divide by an Lz. If I want to make this a complete square, I will have to add minus mu alpha over Lz square. So then this becomes a complete square, but that's an extra quantity, so I have to add that out. So it's mu alpha over Lz square. think so. Okay. So what we have is then this is LZ R over R squared 1 over. I'll keep this as it is, 2 mu E plus mu alpha over LZ whole square. I'll keep this as a single entity. And this one is minus of LZ over R square, or yeah, LZ over R square, or LZ over R, and that is minus of mu alpha over LZ squared. It's a lot of manipulations I went through. Can you go over or any questions at this stage? Oops. Let me make a check on this so that I'm not missing anything. Okay. 2 mu alpha. Yep. Any questions? Okay. So we have to integrate this. So if I were to say that, oh, I want to integrate this, let me do it here itself, right? When I integrate as an indefinite integral, there will be a constant, right? So let me call that integration constant minus phi naught, right? So that's just an integration constant. It should not be confused with phi at t equal to 0 because we have a choice there. It depends on what we call. So we currently it is just a constant, right? And this is an integral. And it's an indefinite integral. And I'll choose this limits by choosing the constant instead of going by the actual limits. So we have to make a substitution. So we make some identification here. Let's have this is a constant, right? This is not R dependent at all. So let me call that a constant. Temporarily, let me call that C squared actually. 2 mu E plus mu alpha times LZ. That's temporarily I'm going to call that. And here now this is a substitution, doing an integral. So let me substitute S is equal to LZ over R minus mu alpha over LZ. So this suggests that ds is equal to, this is a constant, there is an R here, there is a minus LZ dr over R squared. That's nice because that's why I kept it like that. So if I make this substitution, the ds associated with that is exactly the coefficient that is already sitting in there. That was the reason that was manipulated in that manner. And move that a little bit. And that leads to phi minus phi naught, indefinite integral. This is ds minus ds actually. Minus of integral of ds because this coefficient is minus ds over square root of c squared minus s squared. Like it was looking very overwhelming because that was all constants, but when you identify the constant and the variable separate, that's a relatively simple integral. So we just have to substitute. Let's do this integral. So we now substitute s is equal to c cosine theta. This angle is not the angle that our angle is phi, right? The angle that describes the ellipse is phi. So this angle shouldn't be confused. This is a temporary parameter we are putting in. We'll leave it very soon. So ds would be, or actually minus ds would be c sine theta, d theta. So yes.
That s equals c cosine theta. That's, you said that was a substitution.
That's a substitution because I want to do this integral. If you remember this integral, write it immediately. That's sufficient. Okay. I think yeah, if you know it, that's sufficient. I think it will come out as sine inverse, no, cosine inverse theta. That's what this integral means.
And c is the same c.
C is the same C then.
Okay. Okay.
Yeah.
Thank you.
And the need for such a substitution is that you will see that immediately. Why you substitute that is that when you put that in, it's an indefinite integral. So this is minus ds is c sine theta d theta, and the denominator is c squared minus s squared is c squared cosine squared theta. And you notice that this is again c sine theta. 1 minus cosine squared is sine squared theta. C comes out, it cancels out. And that's just integral of theta, d theta. That's theta. So your orbit, technically speaking, is just theta, if you know what theta is. So we have to go back, right? We want our coordinates back, right? We want to write everything in terms of radius instead of this angle theta. So we go back, right? So what is theta is cosine inverse of s over c. So that's equal to cosine inverse of s over c. So what you were probably asking is that, oh, why do I do this? If you know this integral, it will immediately come out this, right? So if you remember what that integral is, that's what that is. Maybe there is a constant separating it. It might be, if you look at the, look at your, what do you call it? Integral table, maybe it is sine inverse c s over c, but remember it can be off by a constant. So sine inverse and cosine inverse is related by a constant. Correct. So it could be like I could have started with sine here, and that's perfectly fine, but then it's off by a constant. Okay. Clear as of now? We are looking for radius, right? S was still a temporary parameter. So we have to go back and put S, replace S with this, C with this, right? And so, or before that, I can say S over C is equal to cosine of phi minus phi naught. That's my solution. And now let's replace S and C. Okay, so we have S is LZ, or let me write this as S is equal to C times cosine, right? So that it's easier to write. So we have LZ over R minus of mu alpha over LZ is equal to C times cosine of phi minus phi naught. C was square root of, so it is 2 times mu times E plus mu alpha over LZ square cosine phi minus phi naught. So we have the answer actually. So notice R is equal to, if I were to put this on the right hand side, R gives you the answer. We are interested in the radius as a function of phi. So we have the solution, but we want to process this. Right? This apparently is an ellipse, right? So let's read this better. So let's do certain things. What do I want to do? Let me take a mu alpha common out. So let me write this as LZ over R minus mu alpha over LZ is equal to, I take out a mu alpha out, and this becomes 1 plus 2 mu E. So this is, what do I want to write this? 2 mu E over this one. So this is mu square, alpha square, and LZ square. Okay. Think so? That's what I want. And that's cosine of phi minus phi naught. Okay, I divide this out. I put this in here. So I write this as LZ square over mu alpha, all in the numerator, divided by R is equal to 1 plus. So these two goes away, so I put the 1 on the other side. And this is square root of 1 plus, there's E divided by, then there's LZ square over mu alpha there still. So how I want to write this is one of the mu's cancel out, and I have alpha over 2 LZ square over mu alpha. If that makes sense. Just a way of writing it, but it'll have meaning. Maybe at this point, just leave it as it is. So let me write this 2 times E LZ square over alpha mu alpha. That's alpha. Okay. Better. And that is cosine of phi over phi. That's all. Let me define a constant R. So there are only 2 constants now, at R naught to be LZ square over mu alpha. And I use R naught because this has the dimensions of position. So whatever this constant is, LZ square, LZ is angular momentum. Remember, if we calculate the dimension of the such of solid R. And this is a dimensionless parameter. This is what is going to become the eccentricity of the orbit. And we will or as of now, it is just a constant. this will turn out to be, and this is R naught, right? So now I can write this as E over R naught. E and divided by 2 times alpha over R naught. That is, alpha over R naught has, like, and this is a special position, and at that point, whatever is the potential energy due to gravity is what that constant is from. So, our solution in terms of these constants is R naught over R is equal to 1 plus E cosine of phi minus phi naught. Which, if you invert this immediately as R as a function of the angle is R naught over 1 plus E cosine of phi minus phi naught. And that's an equation of an ellipse in terms of the relative position of the velocities. So this is an equation of an, I shouldn't say ellipse, so this is an equation of a conic section in polar coordinates. It's not in x and y, polar coordinates R and phi. What is a conic section? Familiar? Or are you lost at this point? Ken, are you with me?
Yeah. Sorry, I was relooking at some of the math. I'm not very familiar with the conic section.
Yeah, conic section is it's kind of nice. So in geometry, somewhere they introduce. So again, if you're not familiar, make it a quiz. Look up conic section, so that you get this nice diagram. But I'll try to draw this here. So that's it. So this is, let's say, a cone. Probably the other way, right? I think of a cone like this, and now take a plane, a perfect a flat plane, and slice this. So if you were to slice it exactly in the plane, so this is a slice of this cone with respect to a plane, and if this plane was exactly perpendicular to the axis of the cone, what is that dotted line? It would be a circle. Can you imagine that? Like, so think of a vertical line, vertical axis, and now I take a plane which is exactly perpendicular to that. If I slice this cone, I'll get a circle wherever it cuts the cross section of that cone. If this is a solid cone, the cross section will look like a circle, right? That's one conic section. Now let's say we lift this angle, like instead of it being perpendicular to the axis, let's say it makes a small angle, and you will see that this intersection now will become like this. Is that clear? And that's an ellipse. If you look for the equation, that turns out to be an ellipse. That's good, okay? So now the only thing we are doing is that we are changing the plane that was slicing the cone. We made the angle a little smaller. Still you are having an acute angle, let's say less than 45 degrees. And now as you increase it, you reach an angle of 45 degrees. And then you imagine what will that be when it is exactly 45 degrees. Until it reaches 45 degrees, what is happening is that this ellipse is getting longer and longer and longer. Right? But once it reaches 45 degrees, it will go all the way to infinity, and it's not going to close itself. Correct? So plane, let's say this is the plane, And let's say this is the angle the plane makes, so this is the horizontal, and this is the angle the plane makes with respect to the horizontal. Right? If theta was equal to 0, then that's a circle. If theta was less than 0 or greater than less than 45 and greater than 0, it's an ellipse. And if it is exactly 45 degrees, it turns out to be a parabola. Okay. And if I increase it further, if I say theta is greater than 45 degrees and less than 90 degrees, then this is a hyperbola. And this classification, all these curves together is called a conic section. And now you see the word conic coming in. So it's a section of a solid cone. And we will see this more explicitly. We will see why that this shows up. Yeah, let me stop here. Okay. So we have shown that this is a conic section. What I'll do next time is I'll start from here, just start from this orbit, and show that if we choose E to be certain values to be an ellipse, or it depends on the energy, right? In our case, these are not, we have to go by the energy. If E was smaller than certain energy, we will get an ellipse and so on, and what to classify that. Since I'm not finishing this, or basically homework is still there, but yeah, homework you're going to decide, right? We haven't reached, actually homework part I won't be covering because homework part was this with Brunjel and Spectre. It's independent, I'm not going to be covering the path at all. So you can decide when you want to. So the next homework will be due the next Thursday. Okay. So, yeah.
So the little e,
Mhm.
that's the eccentricity.
Yes, this will, as of now, I haven't said anything,
Oh, I see.
but this will turn out to be the eccentricity of the conic section of the ellipse, if you want.
Right now, it's just a constant.
As of now, I just call this a constant, but has been labeled appropriately. And R naught is a very special distance. So if you want,
Oh, and for the cone right there,
uh-huh.
does it matter the angle of the cone, right? So like,
I think it
perfect?
has to be 45 degrees. Okay, does it matter? Good question. Like, because somehow it's probably can be scaled.
I see.
I would say that it does not matter, but let me not be very strong about it. Because usually you can scale things out, right? And I can compress this length here and there. I would think it doesn't, but the way I showed it, it seems like, oh, that should be 45 degrees, right? But if not 45 degrees, there's some angle that does that job.
I see.
Yeah. And it's also, I mean, if you want to think, but you have enough homework already, it's good to imagine what is R naught, right? I gave you an idea of what E is. It's going to be the eccentricity. What is R naught? It's a good thing to, like, if you have an ellipse, where is R naught? So we're going to very soon. We have not introduced focal point and nothing as of now, which is just a solution. Right? We'll come up with all this and we'll see where R naught. This is R in general is this. Right? This is your R. Right? R changes with angle. But there is a special point R naught in all this.
The center.
No, it doesn't come out to be the center. So, and it's actually this distance. We will keep it on the other side.
The minimum distance.
Not the minimum distance actually would be this. I haven't drawn
I
this.
see, sorry.
Yeah, no, that's my fault that I haven't drawn it. So if you were to have this, this will come out to be the minimum distance. This will be your R minimum. So basically we can see that, right? When will this be a minimum, right? When will R be a minimum? Whenever this is a -1, right? Because then it is 1 minus. That's a constant. Whenever this becomes a minimum denominator or minimum or a maximum, that's when this will become a minimum or a maximum. Cosine phi can be plus or minus 1. So R minimum and R maximum are not over 1. So minimum will be 1 plus E and R naught over 1 minus E. But that still doesn't tell you that it turns out that this is R naught, which is greater than this. So if you draw this ellipse correctly, so this has to be larger.
I see. And eccentricity is like the squeeze of the ellipse. Right?
Yes, how much it is. So it is actually, so if you again have an ellipse, so this is A, that's your B, right? It is 1 minus B over A.
I see. Where eccentricity is 1, then it's a line.
Then it's a line, exactly.
Okay.
If B was equal to A, then it's a circle.
Right. Okay.
Because E is 0.
I see.
Right, that's a circle. And a good question to ask is how much is the eccentricity of Earth? How elliptic is it? Like, how off is it?
The Earth itself.
Or not Earth, I mean the orbit of Earth. Right? How good, like when we say it is circular orbit, how much error are we making? That's the point. And it turns out that the eccentricity of Earth is about 0.02. So if we are working in 1 sig digit, it doesn't really matter if you say circle. So this R naught comes out to be very close to this point. So, and by the way, this point is March 23rd. This is March 23rd. That is the longest. No, that's the day when everywhere on Earth it is 12 o'clock, like 12 hour, day night.
Oh, wow.
Difference. This is the longest day. Yeah, this is the longest day. This is December. This is December 21st. That's March 21st or 23rd, I think. This is June 21st or 23rd, and this is those are the 4 points. What's that called? Equinox, I think.
Yeah. That's the winter solstice.
Yes, that's exactly. Right. So those are those dates, and then you can ask, okay, that is this point here. How much off are you between these 2 points? Right? And it turns out that's just by a day. It's not a very big difference. If it was a very, like for Pluto, for example, this would be significant. That's very, eccentricity is very large for Pluto. But for Earth, it is just by a day, it is off by just a day. But there it might be significant compared to the orbit of the time period of the. So those are all interesting relations you can get very easily from this. But this is the equation that governs all that. And we'll talk a little bit about all this next time to a certain extent. At least the analysis that is needed. But of course, you can do a lot more. Yeah, so let's stop here, and next class we will do the how ellipse hyperbola comes in, and on Tuesday we will do the how we can get a perihelion of this ellipse to a certain extent if we put a perturbation. Like if there was another planet close by, then how will this perturb this to a certain extent? And then it will start processing. The orbit starts processing just because there is another object.
Which is why people said there must be another mass.
Exactly.
Right.
Exactly. And that is pretty close to what we have today. I mean, if you are aware of this, like one of the biggest unsolved problems in physics today is it is popularized as dark matter. There are two problems. One is dark matter and one is dark energy. So, are you familiar with the word? So, what is happening is that, so I'll explain this. So, very simplistically speaking, but it is exactly like what we had about mercury. So, think of just Newtonian Newton's equation. If you have an object going around another object, right, we have mass times acceleration. It's going in a circle, so it is v squared over r. And that has to be equal to g m1 m times capital M over r squared, right? So one of the r's cancel out and the mass cancels out. And notice that velocity is inversely proportional to r. So velocity squared is inversely proportional to r. That's clear. And the only thing it depends on is the mass inside of the orbit. If it was outside, just by spherical symmetry, it doesn't come in, or it doesn't. It's like a hydrogen atom in the nucleus. So you have to argue that that doesn't play a role. So now let's think of a so this is this disk, or this could be a sphere, or these are all stars. Think of this as a galaxy. This is, let's say this is spinning. This need not be spinning, so the whole galaxy need not be spinning. Each star is actually moving. It has a velocity. Like our sun is going around the center of our galaxy, which is a Milky Way. So each of this velocity has to satisfy this relation. V squared has to be proportional to, has to be inversely proportional to the radius. Now there is also the feature that there is this mass here. So it is, you have to actually account for the fact that mass is all of the mass that is inside the star. Right? Because the outside stars do not contribute significantly. If it is spherically symmetric, then it doesn't contribute at all. So if you take care of that, it is actually not r, because as you grow, there is a mass is growing with radius q, so there is an increase. So if you were to plot this, what you expect is that there is the radius of the galaxy r, that's your r, and that's your small radius r. Right. And if you were to plot this v squared, what you expect is that it will grow. So at the very center, it should be 0. So it will grow. This is theoretical. Okay? It will grow, and then it should go 1 over r. This is outside, and inside, because mass itself is increasing with radius, it grows, and then it should decrease. Great. That's a simple relation. Newtonian physics and Newton's law is what dominates this. There's no relativity coming in there. Nothing is to be accounted for. This is how it should behave. But now it is very easy to go, and these days with our technology, we can actually measure the velocity of all these stars perfectly, very precisely, actually. And it turns out that it goes very well this way. Like in, let's say this r is somewhere here. It's very in the outer region. So, or let's put r itself here. Now, what happens is that theoretically, experimentally, so this is your experimental data. They're all fine as far as you're inside the galaxy, but as you go outside, this doesn't go down. how the data looks. Significantly off. Wow. Okay, so now you say, oh, what happened? So it would have been good if this is not where you had the discrepancy. If the discrepancy was here, then you would say that, oh, that's because at the center we have something very heavy, and that is what happened in hydrogen atom. Hydrogen atom, we didn't know that there was a nucleus and an electron. 120 years back, before Rutherford did his experiment, the model for atom was like this. There was positive charge, negative charge, positive charge. So it was a plumb model, like all the positive charges are everywhere, all the negative charges are everywhere. So that was the model. Then suddenly there was an experiment done, and there the discrepancy was on this side, and they said, oh, the only possibility is that there's a huge heavy mass here, and then no positive. And it explained it. Right? But it was inside. But now you're outside. So what you say is that, okay, there must be a mass outside. So currently the claim is, or if we have to explain this, only by possibility is that all the galaxies have a mass outside, a halo. That mass is not there inside. It's there all outside, and we are not able to see this. Visually, we don't see it because our detectors cannot detect this. That's a claim, right? But it's existing because it's showing this character. So this is called dark matter, which is as of now not detected. That means to say we don't know how to detect it. Like it's like saying there might be something here, but unless we know how to look at it, there is no sensor, we cannot say. And that's just to satisfy that. But if you remember again the mercury, right? We have a data, it is doing something. If it's not doing, oh, there must be something. It's very similar, unless our theory is okay. The other thing is that Newtonian physics completely breaks down in these regimes, but it's not. It's able to explain so many things else, so it's not expected. But then again, remember your mercury, right? Yeah, it was working very well, but then there was this new physics that came up. So that's dark matter, and so the young people like you guys have to think out of the box, right? It's easier to think out of the box for younger people. Older people are biased with the existing theories; they know the theories so well. So think of what can cause that. Pretty simple, and it's an unsolved problem for almost more than I think 70 years or something. So usually these problems don't stay unsolved for such a long time. Yeah. So many people are not able to explain. Yeah.
Hopefully that new telescope that we're putting in the James Webb.
Yes. Hopefully, yeah.
That might shed some light.
Yeah.
I read an article about that over the weekend.
Yeah. And